So in the last sequence of videos, we learned about our two systems of processing information, two systems for categorizing and those same two systems for reasoning. We have system 1 and system 2. System 1 processes information automatically. It relies on familiarity, it relies on similarity, it assigns probabilities based on statistical regularities in the stimulus that you've received, your personal stimulus history. In contrast, system 2 operates deliberately. It might sometimes assign, you might sometimes choose to assign probabilities based on familiarity or similarity, but you don't have to. You can choose to ignore. You can say, look, this is what's familiar to me, but I know that's not what's most common. You can say, look, I know that in my stimulus history, things have been a certain way, but I know they're not that way in general, so I'm going to use some other information to assign a probability. So system 1 and system 2 operate very differently, and our goal here, as I said last time, is to avoid having system 1 push you around. So it's not that system 1's always pushing you in a bad direction, it's just that it's sometimes pushing you in the wrong direction, and you don't want to let it push you around, especially when you're being pushed in the wrong direction. So you want to be aware of how system 1 operates and be able to take steps to avoid being pushed around in ways that you shouldn't. Now, there's a myriad of ways in which system 1 pushes you around, what we might call system 1 level cognitive biases, and they're all important and interesting, but we're just going to focus on a few related to thinking about numbers. And this will give you a gist of how they work, how these biases in system 1 work, and how to combat them when they're likely to push you in a bad direction. Okay, so let's talk a little bit about thinking about numbers. In this video, we're going to focus on one particular cognitive bias, and in the next, we'll focus on others. Okay, so here's a simple problem. You have an experimental here in blue and then a subject in green, and the experimenter says to the subject, 100 people have been given thumbnail descriptions. That's just a short little description. 70 of those people that were given descriptions are lawyers and 30 of them are engineers. Here's one of those thumbnail descriptions. Dick is a 30-year-old man, married with no children, man of high ability and high motivation, promises to be quite successful in his field, and is well liked by colleagues. Now, the idea here is that this description is pretty neutral. It doesn't really push towards lawyer and it doesn't really push towards engineer. It's certainly consistent with both, but it's not just that it's consistent with both. It's that it doesn't really tell you anything one way or the other. That's the idea. Now you ask the subject, what are the odds that Dick is an engineer? And here's the interesting thing. When you're given this kind of neutral description, most people are just guided by the description. So they'll say, well, 50-50 because the description doesn't point in either direction. But of course, as you may have noticed, that's not the correct answer because 30% of the pool were engineers. So the person should say there's a 30% chance he's an engineer because 30 of the 100 people given the thumbnail descriptions were engineers. So that background information that's not in the description, that background frequency, also called a base rate. You can see the word here, that base rate in the population. That is the frequency of the characteristic in the population, the base rate. So this is important even if you have some more interesting background information. So suppose the description added that Dick was a little better at talking than he is at math. Well, that points towards lawyer, right? But it doesn't point perfectly towards lawyer. There are certainly people who are engineers who are better at talking than they are at math. Maybe not a lot of them, but there are some. So even if being a bit better at talking than you are at math points a bit towards towards lawyer, it doesn't point towards it perfectly. Now, suppose the base rate was very different. Suppose we only had one lawyer in our population and we had 99 engineers. And then we get this description, Dick is a bit better at talking than he is at math. Should we say he's probably an engineer because he's a bit better at talking than math and that's characteristic of, probably a lawyer because he's a bit better at talking than he is at math and that's characteristic of lawyers? No, because we just said there's only one lawyer in the population and the rest of them are engineers. So he's probably an engineer because of the base rate, okay? So there's an example where even when it's not a neutral description, it's important to account for the base rate. Okay, so here's the result you get from experiments. When assigning probabilities, many people tend to ignore statistical facts, background statistical information like the base rate, and use only descriptive facts like, Dick is good at talking. And this is a problem because statistical facts are relevant to assigning probabilities, and you shouldn't ignore them. And I should say, System 1 is really driven by descriptive information and really does not tend to take into account statistical facts, at least not in any sort of explicit way, except in, indirectly through your personal stimulus history, which may or may not be representative. But you shouldn't ignore statistical facts when assigning probabilities, so you really need to engage System 2. And you also need to know how to integrate descriptive facts and statistical facts, because sometimes both are informative, so you should be using both. So what do? Well, you always think about statistical facts and learn how to integrate them with descriptive facts. And that's what we'll do now by thinking about some problems where it's a little bit harder to remember to take account of the mere statistical facts, a little bit harder to remember to take account of the base rates. So let's think about a complex case. So imagine this. You have a doctor and you have a patient. And the doctor says, I want to test you for a virus. And the patient says, but I feel fine. Why are you testing me? This is just my annual physical. And the doctor says, don't worry, I'm just testing all my patients. And the patient says, okay. And the doctor goes over and draws some blood. The patient says, ouch. And the doctor says, okay, I've got my sample. We're going to have your results shortly. And the patient says, okay. Well, the doctor goes away, comes back, and says, uh-oh, you got a positive test result for that virus. And the patient's like, what? I feel fine. And the doctor says, you tested positive for the virus. And the patient says, does that mean I have it? And the doctor says, not necessarily. The test is only 90% accurate. And the patient says, so there's a 90% chance I have the virus? And the doctor says, yes, I'm sorry. Well, the doctor's wrong here. And in comes our statistician to tell the doctor that the doctor's wrong and to sort of assuage our patient a bit. So the statistician says, hold on. How prevalent is this virus in the population? This is like the 30% engineer, 70% lawyer kind of thing. This is the background frequency, the base rate. And the doctor says, only around 1% of people in the population have the virus. And the statistician says, then there's only an 8% chance you're infected if you test positive on a test that's 90% accurate. Now I want you to think about that. If you test positive on a test that's 90% accurate, in this example, when only 1% of people in the population have the virus, there's an 8% chance you're infected when you test positive. And I'll explain why that is and explain to you how to figure that out. But I just want you to see how strikingly different that is than 90%, right? Initially, you're like, uh-oh, there's a 90% chance I'm infected because the test is 90% accurate and I tested positive. But now once you account for that base rate, that only 1% of people in the population have the virus, you should actually assign an 8% chance to you being infected given that you test positive. And the statistician is correcting the patient and the doctor, so they're both confused. And here's the statistician's explanation. How many people did you test, says the statistician. And let's just say the doctor says, I tested 1,000. And the statistician says, 1% of people have the virus. And the doctor says, yeah, that's right. And the statistician says, so approximately how many of those people you tested have the virus? Well, it's going to be 1% of 1,000, which is 10. So 10 of the people I tested, I should expect to have the virus, would say the doctor. And the statistician says, that's right. Now, of those 10, how many do you expect to test positive? That is, of the 10 people who actually have the virus, how many times are you going to get a positive test from this test that's 90% accurate? Well, 9. Why? Because the test is 90% accurate, 10 of them have it, so it's going to miss 1. So the statistician says, explain that to me. Why do you think you'll get 9 positive tests from the 10 who have it? And the doctor then says, well, the test is 90% accurate, and 10 people have it, and 9 is 90% of 10. And the statistician says, good, let's write that down. So we've got our test, our 10 people, 90% accurate test, so we get 9 positive tests from people who actually have the virus. Now, how many people who don't have the virus are going to end up testing positive? Asks the statistician. And the doctor says, what do you mean? And the statistician says, well, look, the test is only 90% accurate. So some people who don't have the virus, they're not actually infected, are going to test positive. How many of them will there be? And the doctor says, well, since only 10 of the 1,000 are infected, that means 990 of the people I tested are not actually infected. Because remember, there's only 1% of the population that has the virus. So 990 of the people I tested are not infected. And how many of those 990 are going to test positive? Well, the test is 90% accurate, which means it gets 10% wrong. So 10% of 990 are going to test positive even though they don't have it. And that's 99. So 99 people who don't have the virus are going to test positive. And the doctor says, I guess that's right. And the statistician says, let's write that down too. So now up here we have 10 people who are positive times 90% accuracy equals 9 positive tests from that group. 990 who are actually negative times 10% inaccurate equals 99 positive tests from that group. So this stands for 9 people who are positive test positive, and 99 people who are negative still test positive. So those are false positives. So how many total positive tests do we have? Well, we have the 9 positive tests from people who are positive and the 99 positive tests from people who are negative. So 108. And the statistician says why, and the doctor says, well, 9 infected people test positive and 99 uninfected people test positive. Right. And how many of those 108 have the virus? Well, 9 of them, right? These 9 people up here. 9 of the positive tests come from people who actually have it. So what are the odds you're infected if you test positive? 9 out of 108. And what is that? That's 8%. So we're going to write that down too. We get 9 people who are positive and 100 people, 8 people who are negative will test positive. So the odds you're actually positive, given that you get a positive test, are 9 out of 108. Okay, so I'll stop the video there. We're going to explain this further in a few different ways, but I want to just stop it there so you can sort of ruminate on that, go back and maybe look at it again if you find it confusing before going on to the next video where you'll see some reinforcement of the same problem.